In today's tutorial we are going to learn how to segment animals using the unit architecture. We will use TensorFlow and Keras as well. So we will take a huge dataset of animals and their mask, and we will learn how to use the unit architecture to extract the object out of the image, and then using a new fresh image we can detect and mask and basically extract out the object out of a new and fresh image. As a starting point, we will learn what is the unit architecture. So hope you enjoy this tutorial as well. Okay, let's dive into a unit architecture. A unit architecture is a type of deep neural networks that commonly used for image segmentation tasks. And image segmentation is a process of diving an image into different parts and assigning a label to each detected part. This is useful in various applications like medical image analysis, where you might want to identify and classify different structures within an image, such as organs and tumor. As you can see, this is a U shape. The unit architecture gets a name from its shape, which looks like U when visualize it as a diagram. As you can see, it consists two parts. There is the left part and there is the right part. Encoder is the part on the left side of the U shape. It takes the input image and gradually reduces its spatial dimensions while capturing important features. This helps the network learn high-level representations of the input image. The encoder follows a typical architecture of convolutional networks. As you can see, this is, for example, has 64 filters, and this one has 128, and this one 256. Basically, it consists of repeated applications of two 3x3 convolutions, each followed by a rectified linear unit, a ReLU, and a 2x2 max pooling. For example, this red cross, a 2x2 max pooling operation with a stride 2 for the down sampling. The decoder, this part is on the right side of the U shape. It takes the feature learned by the encoder and gradually increase the spatial dimensions back to the original size of the input image. The decoder's job is to generate segmentation map that assigns a label to each pixel, indicating which part of the image it belongs to. So the key feature of the unit architecture is its use of skip connections. You can see here, for example, is the skips connections. These connections allow information from the encoder to directly reach corresponding layer in the decoder. This helps the network combine both high-level and low-level features, which can lead to more accuracy in the segmentation results. So to get started, we'll be using the Oxford 3T-PET dataset, which contains images of various animals, along with the mask for object segmentation. So let's go to the website of this dataset. I will leave a link for the website. These masks have three types of values: the object itself, the background, and the border around the objects. So let's begin by downloading and preparing the dataset. Please notice that you have to use a torrent client in order to download the dataset. So you can see there are some sample images here. So I can go through these images. These are basically cats. And if I go to the mask folder, you can see that basically you cannot see anything. If I double click of one image, it's a black image. I will explain later what the mask contains. So let's start with creating a new Python file. We will call it step number 1. As I said earlier, I will leave a link for the dataset, so you can use and download to your local machine. Okay, we will start with importing the relevant libraries. As you can see, we will use pandas, OpenCV, and NumPy. We will also set up the necessary variables such as the image dimensions, the number of categories, the file path. Basically, our goal is to create arrays for both training and testing images, as well as the corresponding masks. We will go through the mask values later on, but basically I will leave a remark. The value 1 indicates the main object, the value 2 indicates the background, and the value 3 is indicating the border around the object. I will demonstrate it later on. In this section, we are creating a blank arrays for the images and arrays for the masks. Let's create also arrays for the test images and for the test masks. Let's create another variable for the path. This is the path for the full data set, and we also create a path for the training data and another path for the test data as well. As you can see, there are two text files. One is for the train and one is for the test. Basically, each of these text files contain the list of the names of the images. So we will load these text files, and then we will use this text file in order to load our images. So now we read the dataset training file, which, as I said earlier, contains the names of the image files. We will load and process each image, resizing it to our desired dimensions, which is 128 by 128. And then we will normalize the pixel so the values will be between 0 and 1. This will be by divided it to 255. And similarly, we will handle the mask images, resize it, and categorize the pixel values accordingly. So as first, let's see how many train images. As you can see, it's more than 3,000 images. And now we will start to load the images through the loop of the names, using loops inside the names. First, we will get the full name of each of the images inside the loop. As you can see, each image has it's a JPG file. We will print it just to see the duration, and to see the whole process. We will load the image using a CV2, an OpenCV function called imread. Then we resize it to our dimensions, which are 128 by 128. Then we will resize the values between 0 and 1. And we will also change the type so it will be float 32 and not float 64 by default. And next we will insert our converted image to the all images array. Now it's the part for the masks. We will create the name, the full name of the mask. This is the path for the mask. Please notice that the masks are PNG files and not JPG. We will read the mask using the OpenCV function. But instead of color image, it's a grayscale image. We resize it to the same dimensions. And we will append it, add it to our mask arrays. And at last, after looping through the names, let's print the length of all the images and the length of all the masks. So let's run it. As you can see, we have 3,680 images and masks. So next we will convert the arrays to numpy arrays, since our model works better with numpy arrays. So basically it's running a simple function from the NumPy library. And we will also double check and convert the type of the mask to integer, since it should be only 1, 2 or 3 values. And at last, let's print once again the shape of the NumPy array. So we are expecting to see the same number of images and masks, but it should be a NumPy array. So let's run it. As you can see, we have the first NumPy array is the images, and the second one is the masks. Now let's display one mask to understand what's it built of, the components, maybe the values of the inside the mask. Understand why we haven't seen we see only black images. So what we are going to do is going to display the first mask, which is in 0 position, and we will resize it to 16 by 16. It will help us to print the values and see it on the log. So the pixel values represent the aspects of the image. So after running through all the loop again, as you can see, we have values of 2, 1 and 3. But it's very hard to see where is the object. The value 1 indicates the object, value 2 is the background, and 3 is the border. So it's a little bit hard to see it. So in order to visualize it better, we will adjust the values within the mask. So we replace the values 1, 2 and 3. 1 will be replaced to 0, 2 will be replaced to 22, and 3 will be replaced to 333 respectively. So this will help us better to distinguish between these regions during the training. So let's run through the values inside this mask, this 16 by 16 mask, and we will replace the values as I said earlier. And then we will print again, and it will be more clear to understand where is the object, where is the background, and where is the border. Okay, let's run the code again. And now you can see that 0 indicates the object inside the image, and 22 the background, and 333 the border. It's easy to see. It's after this adjustment, the mask is now actually represent the segmentation categories. So let's continue for the next phase. We already load the train data, and I believe we are ready to continue for the next phase. And in the next phase, we will load the test data as well. We will do a similar process. So we will run through the test txt file, and for each of the values inside it, which is the names of the images, we will load the data and transform the data the same way we have done to the train data. Of course, we will change the name of the arrays and the name of the numpy arrays, but as you can see, we are doing the same process. It's a little bit of copy paste and a minor adjustments. I also noticed that there was a bug with the values of the dimension. Of course, it should be 128 by 128 and not 129. As you can see, there is 129. Let's fix it. Now it's okay. So after we finish creating the numpy array, we will save them to our local disk. We will save the all 4 numpy array, and then we are ready to continue to the next phase, which is the building the model, the unit model. Let's run it again, and after this process will be finished, we are expecting to see 4 files in our local folders. Here are the files. Cool, we are ready to the next phase. Okay, now we are ready to build our unit model. We will create a new Python file. We will call it a step number 2 step number 2 unit model.py. And basically in this section we will dive deep into building the unit model itself, which will enable us to perform accurate object segmentation. And we will start with import the relevant layers. We will use the input layer, convolutional 2D layer, batch normalization, activation, max pooling 2D. The upsampling 2D and the concatenate are both relevant for the second phase of building the unit model. The unit architecture consists of an encoder and decoder structure, which is incredibly effective for semantic segmentation tasks. To begin, we will define the function called conv_block. This function represents a basic building blocks of our unit model that we will use it repeatedly. This block contains two convolutional layers with batch normalization and ReLU activation function. As you can see, this is the second step or the second convolutional layer. We also have an optional max pooling layer by the down sampling. Okay, this is the max pooling part. So now we will define the main function. We will call it build_unit. So this function constructs the unit model architecture. The function takes the input shape and the number classes as parameters. We will start by defining the input layer, and then we will build the encoder part of the unit, okay, the left side of the unit. And this involves a series of convolutional blocks. So we will reuse our function that we wrote earlier. And these convolutional blocks, each one of them followed by a max pooling layer. And this layer will help and extract the consolidated features at a different scale. As shown here, the encoder progressively downsamples the input image and capturing the hierarchical features. You can see that in each of the process, first we are using 16 neurons, then 32, 48, and 64. Moving on, we have the bridge section, which is based on 128 neurons. This is a single convolutional block that captures more complex features from the encoder final output. And this bridge connects the encoder to decoder and allowing the model to learn high level of contextual information. The decoder part of the unit is responsible for the upsampling the feature maps and regenerating the segmented output. Each upsampling steps involved using an upsampling to 2D layer, following by a concatenation with the corresponding encoder feature maps. And this concatenation ensures a precise localization of the features. we are continue with building the decoder part. As you can see, first we have 64 neurons, then 48, and we are continue building the process. Finally, we have the output layer. So this is a convolutional layer with softmax. Softmax is the activation function for categorical problems. And this will produce the probability map for each of the classes. And the function will return our unit model. Let's also create a running script so we can run this code as well. And just to debug it, it's not really creating the model. It's let's say creating the skeleton of the model. So let's run it. We have to fix some uppercase and lowercase. The max boolean 2D. Also the upsampling has a syntax error. Let's fix it on the code as well. Okay, let's run it. We have another error. We forgot the kernel size in the last layer. Let's fix it. Okay, it should be one by one, so we can enter only the one value. Okay, the activation also, it should be activation with lowercase. Let's run it again. Now we have no errors. As you can see, we have the skeleton of our unit model. So let's continue for the next phase, which is training our model. So we will create a third Python code. We will call it step number 3, train.py, and we will import a NumPy array, so NumPy library, and let's copy paste the names of the NumPy array we saved locally. And we will use the NumPy array load function in order to load it from the disk into a NumPy array's variables. So we began with loading the prepared training data, the images, and the corresponding categorical masks. Let's print the shape just to double check that it loads successfully. Yes, it's okay. These masks are converted to categorical format using a one-hot encoding. But before going to this process, let's set up the relevant variables like the dimension and the number of categories. And next, we have to replace the values of the masks, since the values are, as I mentioned earlier, 1, 2, and 3, 1 for the object, 2 for the background, and 3 for the border. And we have to change the values to categorical values. That means that, for example, if we have 3 categories, we should have 3 columns and which each one of them has the value of 0 or 1. So in order to do that, we will use another function of a numpy array. So let's demonstrate it on one image. Let's load the first mask. Then we will convert the values from 1 to 3 to 0 to 2. And then we will run the 2 categorical function to convert it to categorical values. Let's print before and after. So before we are expecting to see values of 0 and 1, and this is the collection, and now you can see it's been converted to 0, 1, 0. For example, 1 in the middle indicates the value of 1. If it was 1 on the left side, that means 0, and on the right side it means 2. So now we have to convert the categorical values for the all masks. So we will run it through all the mask images. First we are converted it from 1 to 3 to 0 to 2 by -1. And then we are running the 2 categorical for the full mask numpy array. Of course, we are sending the number of categories, which is 3. And let's print the type of the mask for model, these new variables. We're expecting to see an integer, and if it's not integer, we will convert it to integer. So let's run it and print it before and after. As you can see, the outcome is float, and now we convert it to integer. It will be more easy for the model. Next, we will split the data into a training and validation sets using the train test split function. So as for test data, we have the relevant numpy array for the test data, but we will split the train data for train and validation. So basically our model will not recognize the test data, only the train and the validation. So as you can see, the test side will be 10%, 0.1, so 90% will be train data and 10% will be the test data. And after splitting the train data, let's print the shapes of these four variables for numpy array. So we are expecting to see 90% on the train and 10% on the validation. Okay, let's run it. As you can see, we have more than 3,000 train images and about 300 validation images. Now let's build our model based on the unit model we built on the second step. As you can see, I'm using a very important line from step 02 unit model. This is our Python code that we wrote that contains the build_unit function. And then we will use this function to create our model and run the training. We also use some early stopping functions like early stopping, reduce plateau and model checkpoints. We are setting up some variables like the shape, number of classes, the learning rate. The batch size will be 4. You can increase it if you have more memory, and we will run about 10 epochs. Then we are creating the model, and let's run the summary just to get the skeleton of the model. Okay, that's good. We have the skeleton of the model. I didn't mention it, but the model checkpoint callback saved the best model during the training. The reduce LR own plateau callback reduced the learning rate if the validation loss goes to plateau. And the early stopping callback halts and stops the training if the validation loss doesn't improve during several, let's say, several iterations, several epochs. So now we are compiling the model. Let's also create two variables. One is the steps per epochs, which is basically the number of images, or maybe let's call it the number of train images divided by our batch size, and also the number of the validation images divided by batch size. This would be the validation steps. Let's choose a name for our saved model. We will call it animals unit.h5. And now let's define our free callbacks model. Early stopping, reduced plateau, and model checkpoints. We will define it now. The reduced model plateau will change the learning rate during the training. You can see the patient's free, it's how many iterations it will wait if there was no change or improvement, so it will change the reduced plateau. And similar for the early stopping. The early stopping will stop the training if there was no improvement during 5 iterations, 5 epochs. And finally, this is the Feit functions, which is the training process. We will record the accuracy and the loss into the history variable, and we are sending several arguments, the X train and the Y train, which are the train images, and the train mask, let's call it the categories, the batch size, which is 4, the epochs, which are 10, then the validation data, which is the images inside the xval, and the categories, the values inside the yval, then the steps per epochs and the validation steps. We also plot or describe the results using the matplotlib library. We will plot on a chart the accuracy, the training accuracy, and the validation accuracy, and also we will plot the loss and the validation loss as well, 2 diagrams. So let's add a little more code, and then we will be ready for the training. Okay, now we are finished and let's run it. We're expecting to see the training process and also the charts by the end of the training. I'm running it a little bit more fast, so it should finish in a few seconds. We are running 10 epochs. As you can see, the validation accuracy is very good. It's 0.8 and it's also improving. Okay, so this is the train and validation accuracy, and this is the loss. You can see that it's a very good results. And we are expecting to see the model saved here. As you can see, this is the name of our best model during our training. Okay, now we are ready to create our fourth Python file. Let's call it step number 4, test the model. So the first step will be loading our saved model from the training. So let's import a NumPy and also let's import a TensorFlow. We also use OpenCV to display the image and maybe do some small modification. So the first step is loading the model. Let's load the model and print the summary. We're expecting to see the skeleton and the weights are inside the model, but let's just double check that the load finished successfully. So it's okay, let's continue. We are using the same variables, the dimensions and the number of categories. Next, let's use the test NumPy array, the one that we saved in the first step. So let's load the images and the correspondent mask of the test images. May I mention it again, those test images, our model never saw it before. Okay, next. Let's convert our model, Okay, the next step, let's take all our test images and let's do the same process of convert to categorical values, to free categorical values. So basically we are taking the images and we are creating like a mask images from our original test images. So let's print the shapes. So each of the images will basically have only 3 values. This will be the first step. Let's print it. Okay, good. Let's continue. So we have about more than 3,000 images. Let's take one image. Just for example, let's take image number 4. So image number 4 was converted to 3 types of values, and we would like to prepare this in image number 4 to our model. So first of all, we will expand beams. What does it mean? We will add another dimension, so it's like be a batch of images. Our model is based on a batch of 4 images, so we are creating a batch with 1 image. Then we'll run the prediction, and then let's see this result mask, the outcome of the prediction. First of all, let's print the shape of the results. As you can see, the shape is 128 by 128 by 3. This 3 is not channels. This 3 is similar to identify or segmentation of the object, the border, and the background for each of these images. So once again, I'm writing this as a remark. These three categories are not channels. It's a little bit confusing. These are the indications for the object, the border, and the background. So how can we extract the object out of this predicted mask? So first of all, let's use the argmax, and it will get the highly prediction values. So it's like taking the best prediction, or the best one for the best mask for our object. We never, as I mentioned earlier, we never saw this object. We don't know what is inside this image number 4. So let's extract the best results. As you can see, it's 128 by 128. We basically creating a new image, which is a new mask image. So let's create another dimension so we can display this image. In order to do that, we will use the expand dims function once again, and the axis would be -1. That means that we are adding the dimensions in the end of the number array. So let's print the shape before and after. So now you will understand that we add in, we will see, expecting to see 128 by 128 by 1. So it's this 1 indicates a value. We are expecting to see 3 values, 3 categories. So let's say multiply it by 255, since an image has a value between 0 and 255. We will also change the type to an integer 8. And once again, let's show the result. The same as the first process when we demonstrate the mask. Let's print the result on a small image, 16 by 16, and let's see the results of the predicted mask. Okay, let's run it. As you can see, the 0 indicates the object, and we have 2 values, 170 and 85. 85 is the background, and 170 is the border. So this is the value of this best mask. So let's change it, and so we can display the result. We'll use the concatenate function of number array. And let's merge several number array together. I think the result will be more understandable. So let's show the results of this concatenate function. So we will display the original image. The first time we are going to display the original image, and then we display the predicted mask. Okay, let's run it. So the first time we have the mask, and this is the original image. Very nice. So basically it's a cat, and you can see the predicted mask. It was very good. We have to do some adjustment to change the colors. Basically the white should be the mask. So we're doing a little bit adjustments in this predicted mask. It will be easier then to extract only the cat out of the original image. So we are changing it to a grayscale image. Let's also, just to double check, let's say, capture how many unique values we have in this image after changing the values or changing to grayscale. We're expecting to see a 3. We are just double checking it. Let's run it again. Yes, we have 3 unique values. Okay, good. So we have to change the values. 170 will be changed to white, and also the 0 values will be changed to white. For us, the border and the object are the same thing, and all the rest will be black. And we are creating a grayscale image of 0 and black, and let's display it. Very nice. So now we have the original image, the predicted one, and we have a full mask. So if we have a full mask, we can apply the mask on the original image and extract the cat out of the image. And this is basically a segmented process. After we created a mask, a predicted mask, we can now extract any cat from any new image. So now we are using an OpenCV function, a bitwise AND, and it will help us to get only the cat out of the original image, and we will display it in the original size. Very nice. It's worked perfectly. Okay. I hope you enjoyed this tutorial. You are most welcome to subscribe my channel for more tutorials to come. Bye bye.